All right. For this week of Instrumentation Lab, I wanted to talk about grounding, which is not a topic chemical engineers really talk about, except that a lot of what we do in industry is going to depend on having good grounds and understanding what that means. And this is just a little tiny piece into it. There's a lot that goes into designing grounds, and I'm literally just going to talk about a couple things as kind of seed topics should you ever need to design a piece of an equipment that needs to be grounded. And so starting out, what I mean by grounding is that something's at 0 volts, and it's basically a safety device. Over here I have the schematic symbol for an earth ground, and we'd like to imagine there's such a thing, and works great for lightning, for example. We drive a copper rod into the ground, maybe 8 feet, at least 8 feet deep, and the idea being that we can discharge lightning. You know, if lightning hits it, it goes into the ground and spreads out, and we like to think that that's done. In your electronic schematics, you'll see this symbol used basically to approximate a ground or an earth ground, and you'll often see it on like the negative side of the battery. So just keep that in mind. The opposite of grounding is what we call floating, where there is no ground. And so the idea behind a floating, and sometimes you'll see it listed as a floating ground, the idea behind this is that we think, you know, maybe we've got a battery hanging out here. We got our 9-volt battery. And maybe we like to think that this terminal here is grounded because it's at the negative end of the battery. But it could be that isn't at 0 volts. It's only at 0 volts with respect to up here. So maybe we have some other piece of equipment over here, and if they get shorted together, we actually do get current flow through there. So that's what I mean by floating. It's just hanging out, not really at true 0. And if you think back to when we were building circuits and all with our integrated circuits and all that, and if you remember, you had your little integrated circuit here, and if you remember right, we powered one and we grounded another. Power, it's like plus VCC, and sometimes you would take a switch wire and you would move it from, say, here around to over here. And while it was in between there, it was unpredictable as to what was going to happen, whether it treated it as a digital 1 or a digital 0. And the reason for that is because what you've done is you made that input floating. And so, because we don't know what's actually happening in here, it's basically like we have a floating point that we don't know what's happening. So that's also why if you were building this and you didn't put this in, you didn't put in the ground wire, it didn't work right. It's because we had this floating point, and that's why I had you go and ground them. So what do I mean by all this? Well, think about your power lines. You're going to wonder why birds can sit on a power line and you can't. The truth is you could if you could climb up there and, you know, fly over to the wire without touching anything else. But the idea is, even though this bird is sitting here at, if it's a standard power line, maybe it's 8300 volts, there's no voltage drop across him. Whereas when you climb up your ladder and climb out onto the telephone pole, theoretically you've got some sort of ground here, like your ladder is connected to the ground or the telephone pole or whatever. So the second you touch this, if this is 0 volts here, and this is, you know, an earth ground down here, and there's 8300 volts here, yeah, there's current flow. Whereas up here with this bird just hanging out, there isn't. Now, if he comes in and tries to step onto the little crossbar there, he will get shocked. So that's basically what's happening there. And so that's kind of earth grounds, but what you'll more maybe more commonly encounter are chassis grounds. And what I mean by that is, you know, any piece of equipment that you got inside of a big metal box, we'd like it so that when you touch the outside of the box, you don't get shocked. I mean, it would be a really exciting world if every time you went to turn on your computer, you got shocked. So what we do is, like right here, you can see we've got this green wire bonded to the side of the box. And so what we've said is this box is basically a chassis ground, and there's our connection point for it. And that's basically so that if something gets shorted out or something like that, we basically can zero it out here to the chassis. And you'll sometimes see this symbol. This is a chassis ground. It looks kind of like the other ground a little bit. But that's basically what that's about. And I'll go through a couple examples of chassis grounds, such as if you look carefully somewhere on your car, chances are there's a wire or this braid here. You see this metal braid that connects to the frame of your car, or in this case, a subframe. But it basically goes from the negative terminal of the battery, so that what we're actually doing is, if this is your 12-volt system, if I put my earth ground, or my the earth ground isn't the one with the E, that's the chassis ground. Now what I can do is I can do things like put my radio in and technically ground it to the body of the car, and it's grounded. That is kind of a poor practice for a bunch of reasons, but you can do it that way. So that's basically a chassis ground for a car. I will throw out here just a couple poor grounds. In a lot of older buildings, you'll find, and even some newer ones, you'll find, you got copper pipes running through the building, and lots of big copper pipes that run out to the street and everything. It looks a lot like an earth ground. And so it's not a terrible practice to ground things to the plumbing. But, I mean, there's some problems with that now, especially if you have PVC or PEX or something like that. Plastic plumbing, it won't work. So it's kind of frowned upon now, but you'll still run across it on buildings that have copper plumbing. But if you look carefully, this thing's just kind of wrapped around this pipe, and it's not actually touching it. It's kind of just maybe kind of touching it, but not really. It's just going to be intermittent, so that's not a very good one. This Inspectopedia place is pretty cool. They got all sorts of horror shows. Also, if you look up here at this one, here we go. We got some copper plumbing and a little bracket to ground to. But notice we've got, this is insulated. We haven't actually, we're not actually making a metal to metal contact, so it's not actually going to work. So there's just another piece. And another thing I wanted to point out was kind of a good industrial practice is anytime you've got two pieces of equipment you want to that are within arm's reach of each other, you want to be able to have them have their grounds tied together if possible. And there's some exceptions to that, but that's generally a good practice. And the reason being, suppose something popped loose here and you lost your ground here. Maybe this is sitting at 120 volts now, but now this one has a good ground. So now, even though you just walk up and touch the two frames of these things, you end up having this path, and so he's unhappy about it. It kind of looks like a mustache, but he's supposed to be frowning. But you end up with this path, this current path, through you, so that's no good. When I was a graduate student, we had two pieces of equipment and had this exact scenario. And the way they were situated, they were little pieces of equipment, and they were sitting on the floor. And whatever undergraduate was there working would basically, to get up, he put his hands on both of them and just kind of push up. And one day we were talking, and had a couple undergrads that worked that position and kind of rotated through. And at some point they all talked about, when we use these powder hoppers, there's this tingle. And when we're getting up, and it's just because we've been sitting so long or whatever. And got thinking about it, and we went up and checked, and between the two powder hoppers, there was 45 volts. And so what they were feeling was actually that current flowing through them. So thankfully it was, that's still a bad amount to be running through you, or to be across you, but Thankfully, nobody was seriously hurt from this, but it is something that can happen. Now, if we tie these grounds together, these two chassis grounds together, if we lose a ground over here, that's okay. It bleeds over to the good ground over here. This guy's happy. All is well in the world. I'll also show you another thing that you may not think about. It's going to be really important if you get into industry. Suppose you've got some tank truck, which I love this. They drew this reflection in here and it's sitting here parked. Anyway, you drive a tank car, or your train brings a rail car, or whatever, or you're pumping stuff out of a big container. What can happen is you can actually build up a charge on these. So this truck's driving all over the place, and just like when you walk across a carpet and build up a static charge, you can build up a big static charge on something like a tractor trailer or a rail car. And you know, maybe something like a rail car, you may have 20,000 volts. Oops, there's supposed to be another zero there. 20,000 volts of just static charge there. And you wouldn't think it. You think, like, how could that be? How could you build that much charge? But it's possible. And it may even be a little lower because you've got a little bit of metal-to-metal contact through the wheels here, but it's not perfect. Whereas on the tractor trailer, you got these rubber tires, it's even worse. So now if you've got this tractor trailer, it's gone all these miles, or this rail car, it's gone all these miles, and you want to pump, say, the propane that's out of it, that's in here, out of it. The last thing you want to do when you are dealing with a flammable gas or a flammable liquid is have some sort of spark due to this static. So one of the very first things you do is you connect a ground clamp to it to keep it from going off. And same with over here. If you've got just lots and lots of fluid flowing through a pump, you can build up a static charge. So you put a ground strap on it. And see, there's our little earth ground over there. These are typically earth grounded, just as a comparison. So there's lots of applications for this that you may not see. But if you're ever at a gas station when the gas truck pulls up, you can look and see, and they'll have little ground clamps that they attach to ground rods before they start filling up the gas tanks, even at your local gas station. So, kind of moving into instrumentation, which we went from really big, like rail cars, to really small. Remember, all of our voltage signals are a voltage with respect to something else. And in a differential mode, it's basically the voltage across some sensor. In single-ended mode, we're assuming that all the sensors share the same ground. So when we did our differential mode, our single-ended mode, we're assuming that these all share the same ground. We're still measuring a voltage across something. We're just saying V1 with respect to ground, V2 with respect to ground, V3 with respect to ground. So we need to make sure when we do this that all these are using the same ground, that's that actual assumption that we can make, and that actually checks out. Otherwise, we really need to go to differential mode to make sure that we're actually measuring the voltage drop across what we think we're measuring the voltage drop. Another thing in microelectronics. So for your guys' chips that you were using, your little integrated circuits, they had some protection on them. But one of the things that I wanted to point out here, this is a in microelectronics, you have to protect everything from static, and static will just mess everything up. And once again, you probably think of static as like, walking across the carpet and touching a doorknob or something like that. And the fact of the matter is, that's a really big voltage by the time you see that little spark and feel that little jolt. You can easily transfer hundreds of volts without feeling it. And so for sensitive electronics, you need to have some sort of wrist ground strap that basically grounds your hands while you're working with it. In fact, a lot of things are being built with a little protection circuit in it. All the integrated circuits I gave you guys, your little NAND gates and NOT gates, they all have a little protection circuit in it to to block some of this static damage. If you don't have that, you can get this situation here, which basically this was due to a static discharge, and this is looked at, you can see that this is through an electron microscope. And I don't 100% know what's happening here because this is a proprietary piece, but what I could imagine is that this is a piece of copper and this is a piece of copper, and maybe this is a piece of copper, and we basically blasted this thing across and maybe shorted out across this piece here, because when we discharge hundreds of volts into something through just a little tiny area, we can heat it up really quickly to thousands of degrees, and basically this metal can vaporize even. That's what some of this splatter is all the way out here, all these little dots. So so the bottom line is, when you handle sensitive microelectronics, sensitive instrumentation equipment, whatever, you need to have a ground strap. This is also true in if you ever go to work in energetics. Something like many a chemist has made flash powder and accidentally set it off early because of a static discharge. And so that's something you've just got to watch out for. You've got to have a way to ground out any charges you develop on your hands. And so overall, in terms of what you need to be concerned about for ground connections, you want a bare metal to bare metal contact. And what I mean by that is you want something where you've got some sort of copper braid or copper rod or whatever coming in, and for like a chassis ground, for example, it's bolted to the metal and there's nothing in between. There's no insulation, there's no paint, none of that stuff, because that's gonna mess things up if you have any of that. It basically, instead of it being you want a nice short solid path to ground without anything else in the way. I knew somebody who was working on electronics for the Navy, and they were doing some work on a helicopter. They couldn't figure out why some of the electronics in the helicopter weren't working, and it turns out they designed this whole system and installed it, but at some point somebody had painted, when they got the helicopter body, they painted it, and whoever installed the electronics just bolted the ground strap right to the painted body, and it wasn't a good enough ground, and so made for a scary flight when they tested that out. So really important to have that bare metal contact. Also, you want it to be thick enough to sustain high currents. So if you do have a major short, you want the current to flow into that ground quickly. You don't want some like little scraggly wire that looks like something that's in one of your fuses so that it just burns up. You want to make sure it's thick enough to sustain like the maximum current you could possibly imagine in that device. And so when we look back at some of those other things, like your car battery had that big braid, so on. And I also say you want to attach it to the largest piece of metal possible. And what I mean by that is that's the point of the chassis ground. If you have this big enclosure, it's really nice to be able to ground to that versus having your current flow to some smaller piece of metal and have this be at some potential voltage there. So that's all I really need to say about grounds. So like I say, it's not a topic that gets covered very often in chemical engineering, but that's because we take it for granted, and it's something that when you're looking around at things, just be on the lookout for. And if you're on interviews at a chemical plant or a refinery or something, you'll be able to see some of this stuff in action. So that's what I have for today.